Hello everyone, and welcome to the new episode of our series of solving LeetCode Daily challenges. And today we are going to solve a problem called least recently used cache, which has a medium complexity. I think it's very fun and educational problem that can really be asked during the actual coding interview. So without further ado, let's move to the problem statement. So we need to design a data structure that follows the constraints of least recently used cache, and it has several operations. So first of all, it has a constructor which sets the capacity of the cache, and it also has two types of operations. The first one is get operation, where we need to return the key, the value by its key if it's in our cache, or otherwise return -1. And we also have a put operation for given key and value, and we need to update the value of the key if key exists in the map. Otherwise, we need to add the key value pair to our cache, and if the number of key exceeds the capacity after this operation, then we need to evict the least recently used key, and that's actually like the core of the idea of the least recently used cache. And very important condition, functions get and put must each run in constant time on average, which is important, and we will use it later on. Okay, so let's solve this problem. Let's start from a very easy case. So imagine that there is no capacity at all, or it's like very big. Then we can maintain a hash map, which can be either an ordered map in C++ or hash map in Java or any other similar data structure in other programming languages. And this hash map will just keep our key value pairs. And for get operation, we will just look up this key in the map. And for put operation, we will just put this key value pair to our map. And this will be a backbone of our solution. It will be present even in the most recent version of our solution. But unfortunately, there is a capacity and we have to deal with it. This means that after put operation, sometimes we need to remove the least recently used key. Not every time, but sometimes. So how we are going to do that? First of all, we'll introduce the concept of a clock. And every time initially this clock is initialized to 0, and every time any operation is performed, the clock moves 1 second forward. So basically we increment our clock by 1. And for each second, we will maintain the key used during the operation performed in that second. And we will keep it as an array-like data structure, which can be either vector in C++ or, I don't know, array list in Java, or just simply an array in any other language, including C++ and Java. So yeah, it will be just an array-like data structure, and I will show it to you how it works in a second. This is not the final idea, but the idea that we have right now goes like this. For get operation, we will just look in our hash map, and we will also, during the get operation, log that during this second, we were interested in this specific key. Okay, and for put operation, we will also log this information that during this second, we were interested in this key. We will update the value in the map, and if our current capacity of the map is now bigger than the capacity given to us in constructor, we will iterate through all of the operations from the earliest as defined by our clock to the latest, and we will take a look. If this key is currently in the map, then we will just remove it and we are done. And if it's not, we will continue our iteration. Let's not worry about complexity right now. We will talk about complexity later on. And that's our current algorithm. It's not perfect, as you will see in a second, but it's something, and it's a step in the right direction. So to figure out why it's not perfect, let's look at the example. So suppose we have this least recently used cache with the capacity of 2, and this is the operations that we are going to perform. and we are going to perform them one by one. So our first, so our hash map with values and keys is called value by key, and we have this operations array that will store operations in order. Okay, so at first we have to deal with operation where for key 1 we put the value of 5. We will add it to our map, and we will also add it to our operations array, and our clock after this operation is equal to 1. And before this operation it was equal to 0, and the zeros element in our operations array is equal to 1 because that's the key of our operation. Okay, our next operation, we are putting 3 for the key of 2. We still can do this because our capacity is 2. So now I will update the first element of our operations array, and I will increment the clock. So yeah, everything quite straightforward. Then I have a get for the key of 2, and I can just look up in the map and return 3. And I will also increment the clock, and we'll add this key that we've just used to our operations array. Okay, the next operation is a put operation. We need to put the value of 7 for the key of 3. Unfortunately, our capacity is only 2. This means that we can, we can add our key, but we also need to evict something, and we also need to log that our clock has increased, and yeah, we have performed an operation on the key 3. Now we need to remove something. So what do we remove? For this, we are going to take a look at our operations array. And the first key that we haven't yet looked at is 1. So let's remove the 1 from our map. And that's exactly what we are going to do. Okay, the next request is to get something for the key of 2. So I will increment my clock, and I will add this value of 2 to our operations array, and I will return the value of 3 from our map. Okay, and now things get interesting. Suppose we have a new request which tells us put the key of 4 and value of 16 to our map. We will do it. We will increment our clock. We will put our key value pair to the map, and now we need to remove something because the size of this map is equal to 3 and our capacity is equal to 2. So what do we remove? According to our operations array, we need to remove the key number 2. But as you can see, it's not the least recently used key. Actually, the least recently used key is 3. So it turns out it's not enough for us just to keep the order of these operations. So what are we missing? Let's keep another data structure, another map-like data structure, where for each key we are going to store the last time defined by our clock when this operation was performed. And then our iteration changes a little bit. When we will consider this key for removal, we will take a look. Is this operation on the key 2 the last operation that was performed on this key? And if it's the last operation, then yeah, we can remove it. And if it's not the last operation, it's not okay for us to remove it, because later on in this operations array, we are going to once again encounter the value of 2, and indeed we will. So let's maintain such a map as well. We are going to call it, how did I call it? Most recent usage. Okay, let me make it readable. Okay, so it's another map where for each key we are going to keep the last time when it was used. So for the key of 2, the last time when it was used is this time, so it has the value of 0, 1, 2, 3, 4. for the key of 3. This was the last time when we used it, and it has value of 3. And for the 4 key, the last time when we used it here, and the time corresponding to this moment is equal to 5. Okay, so where were we? We need to remove something from our value by key map. We are going to look at this item. It represents some operation that happened at moment of time of 1. But for value of 2, the last time when we actually did something with it is equal to 4. So we will just skip it and continue our iteration. Our next value that we need to consider is once again 2. So this operation that we are looking at corresponds to a moment of time of 2. And we are going to take a look. Is it the last time when the key of 2 was used? No, actually the last time when key 2 was used was during the moment of time of 4. So we should skip this operation. Okay, and the next candidate for removal is the value of 3. And the moment of time that we are currently looking at is also equal to 3. And the last moment of time when the key of 3 was used is also equal to 3. So actually we have found our key for removal, and we will remove it from our map. And now our map consists of 2 keys, 2 with a value of 3 and 4 with a value of 6. And as you can see, it's a valid thing. Okay, so let's sum up our solution. So for each operation, we don't care whether it's get or put. We will lock this operation in our system by adding the corresponding key to the operations array and updating this most recent usage time by key map, telling that, okay, now we have performed another operation on this key at a given moment of time. And for get operation, we will just take a look at this value by key map. And for put operation, we will update this map, and then we are going to check if its size is bigger than capacity. Then we are going to evict this least recently used key by iterating through this operations array. And we are going to take a look at each entry in this array and in order and like in a queue. And we are going to check if this operation was the last operation performed on a given key, and we can do it with this most recent usage time by key map. Then we will remove it from our map value by key and stop our iteration. Otherwise, we will continue our iteration. Okay, so let's move to the implementation, and then we are going to talk about the complexity. Okay, so in our constructor, we simply initialize the value of the capacity variable, and that's it. So easy and that. In our get operation, first of all, we are going to log a new operation that was performed with this key. And in this log operation, we will simply push this operation to our operations vector that we have. So yeah, today's implementation is in C++. And we are also going to update this map of most recent usage time by key. And we will tell that now this key was updated during current time or accessed. Okay, so we have logged the operation. Now we need to move our clock 1 second further, which is exactly what we are going to do. And then we will just look up in our map. If the value of a given key can be found in the map, then we will return this value by its key. Otherwise, we will return -1. Everything's pretty simple. And for put operation, once again, we are going to log this operation. We are going to update the value by key. In the end, we're going to update our clock. But also, we need to, if our size of the map is bigger than capacity, then we need to evict this recently used key. And that's what we're going to do. And to do that, we are going to iterate through our operations array. We are looking at an event that happened with a certain key at a certain moment of time. and we need to do a couple of checks. First of all, if this key is no longer in our value by key map, then naturally we cannot remove it and we need to continue our iteration. Then we are going to check if this operation is not the most recent operation performed on this key, then once again we need to continue. Otherwise, we have found our key, we will remove it from the value by key map and we will break from our iteration. Okay guys, now the interesting part. What's the complexity of this solution? So for get operation, everything we do is big O has the complexity of big O of 1, has a constant complexity. So it's quite easy to see that get operation works in constant complexity as well. What about put operation? So everything we do there also works in constant complexity, except possibly of this evict list recently used key. Because here we have an iteration which can take a long time. And indeed, for each certain put operation, it might take a long time. However, suppose we have n put operations, then the size of our operations array is approximately equal to n. And among all of these n operations, we will iterate through each value in this operations array only once. So in total, among these n put operations, this iteration will take no more than n steps, which means that on average, the complexity of our put operation is equal to big O of 1, which is a constant complexity. So this is the idea of an amortized analysis, which we've discussed a couple of videos ago. And yeah, I think it's pretty cool. So as long as among these n put operations, we do no more than n steps in our iteration, then on average, we are good. And this average time complexity condition is very important. Okay, guys, that's it for today's problem. Thank you very much for your attention. I think I tried to explain it in great details. I hope you liked my explanation. If you did, please press like, subscribe to my channel. It's all very important for me. And comment if you have any questions. And have a very, very nice day. Bye-bye.